Alright, in this problem we've been asked to find the inverse of a function f, graph both that function and its inverse. This is the notation for inverse. That -1 has nothing to do with negative numbers. It just means every operation is the opposite, like addition and subtraction are inverse operations. So if we see a square, we would assume we'd end up with a square root. If there was a division, we would assume we'd end up with a multiplication. All of the operations end up being the opposite, the inverse function. That actually helps us know whether we did it right or not, because we can kind of know what to expect before we're done. After that, we're supposed to describe the relationship between the graphs, so we'll see that in just a minute, and then state the domain of each of them. As a reminder, the domain is the description of what x values we're allowed to use. Say under a square root, we would not be allowed to have negative x values. We can't take a square root of negative numbers. We can take a cubed root, we can take a fifth root, but not a square root or a fourth root. If there's a fraction, we are not allowed to have a 0 in the denominator. That's undefined. So we have to look at this. We can't tell at the beginning until we're all done what this would be, and they're not necessarily going to be the same between the original function and its inverse. Sometimes they are, sometimes they're not. Alright, so first let's go through finding the inverse. So here's a function. We've got f of x equals x cubed plus 1. Again, you can kind of tell what the answer should look like when we're done. All the operations are going to be the opposite. So here I see there's an addition. I would expect to see a subtraction when I'm done. Here there's a cube. I would expect to see a cube root when I'm done. The method that we use to find the inverse of a function is referred to as the switch and solve method, and it pretty much tells you what to do. We're going to start off writing this. Instead of using the f of x notation, we'll just use a y. So here's that equation. We're going to switch these two. So the x goes here, the y goes there, but the cube's going to stay over on this side. So we're going to have an x equals y cubed plus 1. So there's the switch. Here's what it would look like. Now solve. What we're solving for is the y value. So we need to move the 1 to the other side. We'll do that by subtracting. Remember, I told you we'd see a subtraction. Then we don't want y cubed, we want y, so we'll have to take the cubed root of both sides, which again I mentioned we're going to see a cubed root as part of our inverse function. So we go ahead and subtract the 1, and then we'll take the cubed root of both sides. And now I have an equation. I have y all by itself. Now that I have a y all by itself, I can substitute back in my function notation, but this time what I've done is found the inverse. So instead of f of x, I'll use f inverse of x. That's how we read that, f inverse of x. This is the inverse function. I found it by using the switch and solve method. That's how you always find inverses, switch and solve. All right, that brings us to the graphing part. So I'm going to first graph the original function. I have it in equation form here, y is equal. That's what a cubed function looks like. It's been translated up 1. Now I'll go ahead and graph the inverse function. And you'll notice it kind of looks the same. It's different, its placement is different, but there's a lot of similarities between these two. What happened here is all of the x coordinates and y coordinates just got swapped, got switched. That's part of how we get that name. That's what an inverse does to the coordinates. Here we had the coordinate 0, 1. Here we've got the coordinate 1, 0. And you could continue that in both graphs. You could just go back and forth. The x and the y values of the coordinates just get switched. Because that's true, I can take you to the next part and describe the relationship. Since they just get switched, there's a line always right here. This is the line y is equal to x. Y equals x. That represents everywhere that y is equal to x. Here x is 5 and y is 5. Okay, so that's what that line represents. Since to find the inverse we're just switching the x and the y coordinates, everything is a reflection across the line y is equal to x. A reflection in a graph just means they're the same distance perpendicular. So you take this distance and this distance, that distance. They're the same, if I could just draw a little better. The perpendicular distance here and the perpendicular distance here, they're going to be the same. It's like when you're standing in front of a mirror. The distance you are from the mirror is the distance it looks like you are behind the mirror. That's what we're talking about a reflection. So all of the points get reflected across the line, y equals x. That's the relationship. That's always the relationship. Last, let's state the domain. Again, the domain is what can the x's be? In our original function, there's no issues as far as undefined things like negatives under a square root or fractions with 0 in the denominator. If we were to make this graph bigger and bigger and bigger, x's could be any value you want them to be. So the domain could be from negative infinity all the way to positive infinity. When we look at our inverse, at first you might think, oh, there's going to be issues here with negatives. We have a radical. Except this is a cubed root. We can go ahead and find values when there's a negative under a cubed root. So there are, again, no restrictions on that one. So our domain for both of them is going to be from negative infinity to positive infinity. Again, that's the values on the x-axis. We can go from negative infinity over here to positive infinity over here.